All, welcome to our channel Way to Know. In this video, we will talk about a very popular circuit which is called a trans resistance amplifier, which basically is also called trans impedance amplifier, or in simple terms, current to voltage converter or I to V converter. So the purpose of this particular circuit is to generate output voltage based on the current that is being sensed as input. So where do we use this? Basically, let us assume we have a sensor like a photovoltaic cell, or you can say photo transistor. All these which produce a current output based on the sensing that happens will be input to this particular circuit. Actually, here if you see that sensor is modeled by a current source here, okay, and this input is further amplified by this particular circuit and transformed into a voltage output, and this can be further given to any microcontroller kind of circuit, which actually converts into a digital value using the ADC. This is the basic of this particular circuit. Now for this we have a op amp, and op amp basically acts as an amplifier here, and this is a dual voltage op amp OP777, where to the positive terminal we have given plus 3.3, to the negative terminal we have given minus 3.3. That means the entire swing that is possible for this particular op amp is minus 3.3 to plus 3.3, and then the output of this particular op amp is determined using this particular formula, which is I into R2. So why I into R2 is whatever the current that flows here, actually as this is a very high resistance, the current flows through this 5 mech feedback resistor, and that gets converted into the output voltage. So that is why the current that is input into the feedback resistor is nothing but the output voltage. That is straightforward. Now there are few things which we need to do before working on this particular circuit or confirming the circuit, or we can say some design steps involved. What are those? So the first thing, you see a resistor here. This particular resistor is actually required, especially at the startup of this particular op amp, such that there is a stable voltage here. Okay, that is a primary requirement. And then second thing, we also see a feedback cap in parallel with the main resistor, and this actually is required to maintain the stability of this particular op amp. So what happens is there will be some capacitance associated with the source that is connected. The source can be anything, right? And then there will be some pin capacitance. So these two capacitances has to be compensated, and to ensure that there is no distortion or noise that gets introduced, this capacitor is added in the feedback such that we eliminate any noise that is there. And second thing, this capacitor is selected such that we have sufficient bandwidth for this particular op amp. What do you mean by sufficient bandwidth? So we are having this sensor, right? This sensor is not stable always. This is a input which varies. So there will be a maximum frequency at which this will get varied, right? So that determines the maximum bandwidth or the maximum frequency that is input to this. So this capacitor must be used such that the bandwidth of this op amp is more than what is required. So that is determined by 1 by 2 pi R2C2. So we have to ensure that the capacitor doesn't add unnecessary restriction for this particular circuit. A very, very important parameter. And so we talked about the feedback capacitor, we talked about the resistor here. we talked about the type of sensor. The major point is the selection of this op amp. Okay, so the selection of this op amp is a very critical criteria here, because you have a negative output, which is the inverting terminal. If you want to see a swing on the output to a negative side, so that you actually know that this is the actual value it is reaching, you need to have an op amp with a dual supply. Okay, that is why we see plus 3.3 and minus 3.3. And ensure that you have the bias current of this particular op amp, which can detect low currents. And also the resolution is a primary criteria. So you have to select this particular resistor such that the current here will actually be above the input offset voltage of this particular op amp. Otherwise, you miss out on that resolution and you may not be able to detect the input voltage. And ultimately, what you see here out at the output is a noise which is not the true reflection of the sensor output. Okay, so these are the very important parameters which need to be considered while designing this current to voltage converter. Okay, now let us simulate this. Okay, let us try to read this particular voltage, this particular node, and this particular node you see here, it's around 20 millivolts, and you can see a kind of sawtooth waveform here, right? This can be eliminated by varying your resistance and the capacitance that is present in the feedback, such that you have proper rise time and fall time, and the state is maintained. So that is very important design parameter. And then once you click on the output, you see the output has gone up to minus 2.5. So if you go back, the output is determined by minus I is calculated using minus I into R2, right? I is nothing but the current that is input, and R2 is the feedback resistor. So if you combine, like we have 500 nano amps of current here, that means 0.5 microamps. And if you see into 5 meg, which gives 2.5 volt. So the output you see here, and it is on the negative side, right? So it goes up to minus 2.5, and then once the input reaches 0, because the input is a pulsed input, right? It's not a continuous 20 millivolt. So that is why you see a fluctuation on the output corresponding to the input voltage here, which is explainable, right? So and then you can actually play around with the capacitor to see how it is adjusting, and also change the input frequency in accordance with your sensor, and see how the circuit is behaving. And this kind of simulations are very important when you are working on the design, because you don't know what sensor you'll be connecting, so you'll be testing that sensor interfacing with your circuit only when the final circuit is available on the board PCB, right? So before itself, we can model all the parameters. We can also include the capacitance of this particular sensor, the trace capacitance of the PCB as well, and the pin capacitance. Anyway, pin capacitance will be part of the model. So all these can be included here along with the final capacitance, and we can actually simulate this to adjust the feedback resistors, capacitor, and the input resistor. All these can be changed. And in case if you find that a particular op amp doesn't have this resolution capability, we can actually change the op amp and then calculate the output voltage. A very, very simple circuit, but has lot of design guidelines associated with this. And please let us know if you have already worked on this, if you have any suggestions on this video, and any problems that you have faced with this circuit while working on it. Thank you.